This tutorial will explain what standard deviation is, how it is calculated, and what else should be considered within this context. Standard deviation is a way to understand how much the values of a variable tend to differ from the average value, aka the mean. It tells us how spread out or close together the values are. If the standard deviation is low, the values are close to the mean. Conversely, if it is high, the values are more spread out. Mathematically speaking, you are taking the square root of the average of the squared differences from the mean for each individual. To illustrate and also calculate this, we can hop straight into an example. Imagine we have 10 participants complete a standardized task, and we measure how long each one takes to finish. You can see we have some faster and some slower participants, ranging from 29 to 50 minutes. To get to the standard deviation, the first step is to calculate the mean in order to see how close or far the observations are from the mean. The formula for mu is given in a somewhat cryptic form. Simply sum up the values of all observations and divide this by the number of observations. This means adding up 33, 50, 44 and so forth, which will give a total of 380. This sum is then divided by the number of observations, which is 10 here, and you'll get the mean of 38. This allows us to calculate and visualize the differences between the individual times and the average time mu. Individual A is 5 minutes below the average of 38. Individual B is 12 minutes above, and so forth. Individuals that are very fast or very slow show larger differences from the mean. The standard deviation mathematically summarizes those differences and puts it into one single number. The second step therefore is to square those individual differences. -5 squared makes 25. 12 squared makes 144, and so forth. All squared values will obviously be positive. The third step is to sum up those squared differences. 25 plus 144 plus 36 and so on. The sum of squared differences is 436 for my example. The fourth step is to calculate the average squared difference. This means simply dividing the recently calculated sum by the number of individuals or observations. Spoiler, we will briefly talk about an exception a bit later. The average squared difference is also known as the variance, which is denoted sigma squared because of the squared differences. For my example, the sum of squared differences of 436 is divided by the number of observations, which is 10, giving an average squared difference of 43.6. The fifth and final step is to take the square root of the average squared difference. In my example, the square root of 43.6 is 6.60. On average, the individuals deviate by 6.6 minutes from the mean of 38 minutes. You would not have been able to say that by using the variance of 43.6, because we can only interpret the average difference in a meaningful way, not the average squared difference. The green interval is a graphical representation of the standard deviation around the mean for my example. I mentioned earlier that dividing the squared differences by the number of individuals has an exception. Actually, that exception is the rule. Let me elaborate on this further. Usually we have a sample and do calculations and hypotheses testing based on that sample. We then draw conclusions about the entire population. In the unlikely event that you have data for the entire population, you can use the standard deviation calculation, sigma, I just showed you. If you only have a sample, which is more common, you need to correct for sampling bias. This rings true the smaller your sample is. For very large samples though, this bias is usually negligible and dividing by n alone is generally accepted. To correct for sampling bias, use n-1 instead of n when dividing the sum of squared differences. If we apply this to our example, we would divide the sum of squared differences of 436 by 9 instead of 10. This would eventually lead to a slightly higher standard deviation of 6.96. This illustrates quite well that using the unbiased version of the standard deviation usually results in a slightly higher value compared to the biased version. To sum it up, standard deviation and variance both measure the spread of a variable. The variance is the average of the squared differences from the mean, while the standard deviation is the square root of the variance. The standard deviation is easier to interpret because it is in the same units as the original data, whereas variance is in squared units.